Welcome to Old School Chemistry. Today we are going to do the topic from ALEKS called Interpreting a Skeletal Structure with Aromatic Rings. Let's look at aromatic rings. It's really just benzene. In the early 1800s, scientists called these aromatic because many of the aromatic compounds had a smell to them, and the name just stuck. So that's where the word aromatic comes from. Don't let that throw you. It's really just looking at benzene. And remember, benzene is C6H6. Now, I drew out the complete structure for you. We have 6 carbons that are in a hexagon. And what makes this aromatic is that you have alternating double bonds. I have a double bond here, single, double, single, double, single. Now, check this out. If we count bonds just around the carbon, you've got 1, 2, 3, which means each of the carbons has 1 hydrogen. Now, a fascinating point on this. Every single carbon has 1 hydrogen. So let's count electron domains. That means that you have 1, 2, 3 electron domains. And what's the electron geometry for 3 electron domains? Trigonal planar, which is going to be, in essence, 2-dimensional. It's flat. What's a special point about these is that they're flat. These are going to be flat molecules. And because of the double bonds, is also going to have p orbitals. That makes aromatic rings very unique, okay, very, very unique. Now, because we have these double bonds that resonate, we actually write this 2 ways. I can write it this way, so now I've just put it in the skeletal structure where I'm only showing the vertice indicating carbon, and we know that there's enough hydrogens to make sure that carbon has 4 total bonds. So our skeletal structure, I've got my 1, 2, 3, 4, 5, 6 of my carbons. They are double bonded, alternating single bonds, which means this resonance structure, that double bond will resonate and come to this single bond. That double bond resonates, goes to that single bond. That double bond resonates and goes to that single bond. I do this with my students, that this will go back and forth, back and forth, back and forth, back and forth really fast. So we write it with both resonance structures. I can write it this way, and then also where the double bond will resonate to. That where we have double bond, single bond, double bond, single bond, double bond, single bond. Say that fast 10 times. Now, there's another way to write this. Because those double and single bonds resonate back and forth, another form of writing an aromatic compound, writing a benzene ring, is just put a circle, meaning that the double and single bonds are going to switch places, resonate back and forth. And that's where we pick up on ALEKS. So let me show you this ALEKS topic. It says, answer the questions in the table below about this molecule. What is the molecule's chemical formula? Here's what I recommend you do. I would rewrite all of these problems are going to write the benzene ring, the aromatic compound, with the circle. I would rewrite it so that you can see the double bond and single bond. That's one option. Or second option, you will know that every carbon has a hydrogen on it attached to it. Let me do this both ways. Okay, we're going to figure this out both ways. So I would take this and I would rewrite it so that I can see the double bond and the single bonds. And it doesn't matter which way. If I start with the double bond here or the double bond there, doesn't matter. Okay, just alternating double and single bonds. Then we're going to have a double bond to our oxygen, and then another aromatic ring, that benzene. Okay, now I can start counting my carbons and hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we're going to have a C13. I counted my carbons in this compound. Now we can look at hydrogens. Okay, figuring this out, remember, I have enough hydrogens to ensure that carbon has a total of 4 bonds. So I'm going to count bonds right now. I can see on this carbon there's 1, 2, 3, which means there's 1 hydrogen. Look here, 1, 2, 3 bonds, there's another hydrogen. 1, 2, 3 bonds, there's another hydrogen. And you can see that we've got 1 hydrogen, 1, 2, 3, 4, 5, on each of the vertices, where the carbon in the aromatic ring, you and I know, has 3 bonds. So I've got 1, 2, 3, 4, 5. Now look at this carbon right here. It doesn't have any hydrogens. It has 1, 2, 3, 4 bonds. That is our tertiary completely consumed with carbon bonds, okay? Let's see here. This carbon, 1, 2, 3, 4, completely consumed. We don't have any more, is completely bonded, 4 bonds. We don't have any room for hydrogen. Same thing here, 1, 2, 3, 4. 4 bonds, there's not going to be a hydrogen on that. So our hydrogens are going to be 1, 2, 3, 4, 5, and then come over here, 6, 7, 8, 9, 10. So that will be an H10, and then we've got our oxygen. So that's what I would type in here. I would do the C13H10O. And then down here it says how many CH3, CH2, CH groups do we have? Well, let's look. We don't have any CH3. There are no just, hey, here's a carbon with 3 hydrogens on it. We don't have any carbons with 3 hydrogens. In fact, we don't even have any carbons with 2 hydrogens. All of the hydrogens are bonded to carbon with 3 total bonds, and so there's 1 hydrogen. All of these, all 10 of these, each of these is going to be a CH, carbon with 1 hydrogen. Each of those, all 10 of those are carbon with 1 hydrogen. So over here, let me scroll this up just a little bit. I would put a 0, and then I would put all 10. Now let's go ahead and hit explanation just so you can see the answer. There we go. Beautiful. Look at that. We've got our C13H10O, and then we had the 10 of the CH. Now, we took the time to draw this out. Let's do one where you don't draw it out. And you and I know, okay, we know that in that benzene ring, in that aromatic compound, that each carbon has 1 hydrogen, okay, as long as it's not bonded to anything else. So let's look here. I'm going to go ahead and draw on this, okay? I see my 2 aromatic rings. Now, a little side note, there's a bond here and a bond here going out to the 2nd aromatic ring. That takes care of that 4th bond. If I look right here, okay, watch this. I know that I have a double bond here, like that. That carbon would have 1, 2, 3, 4. 4 total bonds to other carbons. So I know if the vertice is just the carbon, there's going to be a hydrogen on it. But if it's bonded to another carbon other than my aromatic ring, then I don't have a hydrogen, because that second, or this bond over here, that took the 4th bond in essence. There's no more hydrogens. Look at this one up here. This would have 1, 2, 3, 4. So there's not going to be a hydrogen on that. Look at this one right here. If I had a double bond right here, you'd have this carbon would be 1, 2, 3, 4. It has to be a vertice with nothing else bonded to it for it to have a hydrogen. For example, if I have a double bond here, it'd be 1, 2, 3. That means I'd have a hydrogen. I'm going to draw the hydrogens for you. Okay, I'm going to draw the hydrogens for you. So we'd have a hydrogen here, here, right there, and then over here. Those are going to be our hydrogens. It's that vertice where you know there's a double bond on one side, a single bond on the other, 1, 2, 3 bonds on that carbon, which means there's 1 hydrogen to get the 4th bond. So this, adding it all up, those 2 carbons, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this would be a C10. And then hydrogens, we've got 1, 2, 3, 4, 5, 6, 7, 8. Can't miss the hydrogens on the alcohol groups. And then we've got the 2 oxygens. So that would be our chemical formula. And then I don't have any carbons with 3 hydrogens. There's no carbons with 2 hydrogens. I've got 1, 2, 3, 4, 5, 6. 6 carbons. I do a CH. I've got 6 carbons with that CH. I think we need to do one more. I think we need to do one more. Let's do one more together. Okay. I'm going to go ahead and do explanation so you can see that answer. Beautiful. That was what we got. Let's do more practice. And let's see. Do you know what? That's too similar. Let's do a different one. That was really similar to what we just did. Okay, like this one. I am going to start counting hydrogens. I know that hydrogens on this aromatic ring, I have one hydrogen for every vertice that's not bonded to anything else. So we would have 1, 2, 3, 4, 5, okay? So I'm going to put down, in fact, let me just do the lines. There would be a hydrogen, 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 hydrogen. I'm not going to have a hydrogen here because that carbon would have 1, 2, 3, 4. It would have 4 bonds. 4 bonds to other carbons. Now let's look at this carbon. This carbon has 1, 2, which means I have to have 2 of my hydrogens. And then this carbon has 1, 2, 3, so there's a 4th hydrogen, that 4th bond. This carbon has 1, 2, 3, so there's going to be a bond. And then this carbon, it's at the very end. It only has 1 bond, so this is going to have 1, 2, 3. Okay, let's go back and count the hydrogens. We'll end up with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's going to give me H12. Let's check our carbons. I have 6 carbons here, 6, 7, 8, 9, 10. No oxygens. So this would be my chemical formula. It's C10H12. So glad we got this one. Now down here, look, I actually have 1 carbon with 3 hydrogens on it. Right there, we've got 1. And then here I have 1 carbon that has 2 hydrogens on it, so I put 1. And then our carbons with 1 hydrogen, we've got 1, 2, 3, 4, 5, 6, 7. And then I put a 7 right there. Okay, good. It just takes a little bit of practice. If you need to, write it out with the double and single bonds. That can be a little bit easier. Once you do this several times, though, you'll get the hang of it that there's 1 hydrogen on each carbon as long as that carbon isn't bonded to anything else in the aromatic ring. I'm so proud of you. Thank you for joining me. So appreciate it. If you haven't, please like and subscribe, and I'll see you next time.